This is the decision one paper from 2022, Pearson Edexcel. Let's just do this. We're cutting these lengths, calculate our bounds. So just add all these up together. You get this. Divide by 10 because that's the each ball that you have, and you get this. You round up to 4, so the lower bound is 4. Use the first bin algorithm. So in the first bin, you'll put the first thing. You can go up to 10 here. So this isn't going to fit in the first bin because that adds up to more than 10. So you go to that in the second bin. Then this that can go with that. That's less than 10 when you add those two together, so that goes in the first bin. That can't go with either, so that goes in the third bin. This, again, you go from the top downwards. It can't go in the top bin because that's too big together, but you can go into there. And then this one needs to make its own bin. This one can go in, I think, with this bin down here. Yeah, it can. And then 1.7, I think, can go with this one, it looks like. Oh, no, it can't quite fit in there. It goes in this one. I think there's like 1.4 left over in there. So it goes in this one instead. There's very little left in here. 2.1 has to go all the way down here. 0.4, I think, can just about squeeze into there, and 1.3 squeeze into there. And that'll be how we're going to pack that in. Question number 2 about Dijkstra's algorithm. So they give us all this to work with. We'll start with 1, 0. We'll do an 8, an 18, and a 14 to get there. The smallest one is the 8, so that'll be the second place we go to that takes 8. Then we'll go 8 plus 9 gets us a new distance here, 8 plus 23 there, 8 plus 4 there. And we'll choose the shortest distance of all the 4 available ones, which is going to be this one, so that's going to be our third place. That takes 12 to get to. And then we add 16 to get to here, we add 31, we add 17, we add 3. All of those things get added to 2, and to 12. And we get all of these values. Again, pick the shortest one in any box that you haven't been to, which I think is this one, so that'll be 4 and 14. Add 14, add 25, and we get there and there. The shortest one now, I think, is this one, so that'll be 5 and 15. We can't actually go anywhere that we haven't already been from there. Oh no, we can go there, so 15 plus 10 is 25. And that's actually the shortest distance we can go to, so that'll be 6, which will be worth 25. Then we add 10 to get to 35. I think that's the only place we can go that we haven't been from here, so that'll be the next one, I think. 28 is the next one, that's going to be 7. 28, add 23, add 33, add 6 to get all these values. And the next smallest is this one, so that will be our 8th place at 34. Add 10 to get 44, add 25 to get 59. That's the next smallest, that'll be number 9 at 44, and then this is the next smallest, 10 for 59. And so the shortest path, we need to get to K, so how do we do that? I think it was A, B, E, and then I think we went H, G, K, I think was the route. Yeah, it looks like it. And the shortest path was 59. Good. The cycle tracks now need to be inspected, so this is a different question. Now we need to use all of the tracks. And now what this is about points with an odd number of routes coming out of them. Because if you imagine trying to use all 3 tracks going to D, you have to go to D along this track, then you have to leave it again, but then you're going to have to go to it again to cover this track, but then leave through another one again. So when you've got an odd number of nodes, you have to use a track twice, minimum. Now, this one has an odd number of nodes, so does this one. So AD, I think E did, and so did H. I think those are the 4 that did. Now you're told you're starting at D and finishing at E, and that's the only time you don't have to repeat. Because if you start at D, you can leave via this route maybe, and then later on come in again through there and leave again through there, and then you don't have to use any of the tracks twice. So the fact that we're starting in D and finishing in E means that we need to repeat the ones going to A and H, which essentially just means we need to find the shortest route from A to H, and we can just repeat that. And the shortest route from A to H, we actually have up here, I believe, is 28, and it's the route that I think goes, does it go here, here, does it go here, 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 A, B, E, H? So we're going to repeat, so we're going to do a bunch of stuff to get around, and we're going to repeat this journey here, so that we can leave and get back to H again, or get into H again, via repeating those paths. So we're going to repeat those paths, which is a journey of 28. We're going to add that onto the 299, and we'll have this total route length here. It's now decided that we have to start at A and finish at K. Now, finishing at K is awkward, because if you finish at K, that means you're going to have to, like, if your last bit was this, and that's the end of your route, you have to use this one twice. So this actually adds in a node that's going to have to be repeated, that essentially has an odd number of routes attached to it, because this is your finishing route. You only have one left, and that means you have to repeat that one somewhere. So okay, if we finish, but we're starting at A, so we removed the trouble with A. But that means we still have essentially odd nodes of D, E, H, and K. because again you're removing that last node, so it's, that last root, so k essentially is an odd thing now again. And now we just combine these up, so we say, okay, we could repeat the journey e to h, d to k, and d to k, or which is 16 plus 25. And you haven't done any proper algorithm to sort this out. You just have to inspect it really carefully, I think. So e to h, well, it's the shortest way from e to h is 16, and then d to k. Just look really carefully. It's not 25 plus 25, or maybe it is. But just make sure you inspect everywhere really carefully and make sure you can't get there any faster. I think that becomes more of an issue here. So when you choose E and D and H and K, for instance, E and D, it's tempting to just do 17 plus 14, which is 31. But actually, if you go, I said 26 is the shortest. Let's see if I can find this. Well, 3 plus 10 plus 14 is actually 27. So there's apparently a way to beat that route, which seems unlikely just looking at this. How on earth did I beat that route? Is it 4? There it is. 4 plus 8 plus 14 makes 26. So you just have to do some really close inspection and make sure that you actually come up with the minimum paths here. And then you combine the last two, you get this. Again, inspect really closely to find these numbers here. This is the shortest one, so this is the thing we'll choose to repeat. We'll choose to repeat the journeys E and D and H and K. So that will be what we repeat, and then we'll just do 299 plus these repeats here for our shortest journey possible. Number 3 then is about Floyd's algorithm. So it just starts, all it wants us to do is put this picture into here. So A connects to B, C, D, E, and F, so we'll put some lines in there. And A to B is 12, A to C is 32, this isn't very complicated, we put them all in. The only thing to be careful of here is notice that A to E you can do is 29, but E to A you can't do, which means this must have been a directed path, just like these ones are. So just be really careful to not do that completely on autopilot and read it kind of carefully. After you've done a couple of iterations of Floyd's algorithm, so they've presumably iterated through A and B so far, they want us to do a couple more. So we're going to start iterating through C this time. So we'll start iterating through C, so we'll keep the C row and the C column the same. And we'll just check this. So A to B, for instance, is currently 12. You don't have to fill in the other table, which is good for me because I'm in PowerPoint and that's really annoying. So we're just filling in the number table. They don't need all the letters next to it in this question, which is nice. So A to B then. Well, A to B is currently 12, is going through C faster. Well, A to C is 29, and then C to A is also, C to B is 17. Those two numbers add up to make way more than 12. In fact, if this number is bigger than this one, then it's not going to work. So likewise, A to D is going to stay at 20 because you have to, otherwise you'd have to go A to C, which is 29, which is already bigger than 20, and then C to D, which is very short, but it's clearly these two numbers are going to be bigger than 20, because this is. Next one is 29, again, that's not going to be any better, because that's 29. And last one is 11, so none of those end up changing. But the B row might do, because 17 is a bit less. So B to A is currently 12, well that's not going to change, because that's too big. Ready? B to D is 8, so that's going to change now. 41 here. So what about B to C, that's 17, plus C to E? Well, 17 plus 12 is 29, so that's going to be much less than 41. And then 23 is supposed to be here now. 17 plus 40 is much bigger than 23, so we'll just keep the 23. And we'll keep going. D to A then, can we do it? Well, currently it's D to A is 24. D to C is only 4 though, and then C to A is 29, so add those together to get 33, and that's no improvement. Next one is 36. D to C is 4, plus C to B is 17, so that adds up to 21, which is a big improvement, so we'll keep that. Next one is D to E, which is currently 53, so it looks like we'll improve on this. We can go D to C is 4, and then C to E is 12. Add those together to get 16, and we've got a big improvement. Last one is 13. D to C is 4, and then C to F is 40. That makes 44, which is much bigger than 13, so we'll keep 13. And we'll just keep going. The infinities we can definitely improve on, right? Because we can actually find a root. We can just do 12 plus 24, which is, no we can't, sorry. 12 plus 29, sorry I've misread it, to get 41 I believe, and then we'll just keep going. I won't be too careful about this, I think I've made my point as to how to do this. You complete the table, just doing everything exactly the same, and then you need to do the fourth iteration, where we keep the D row and column the same, and exactly the same thing. So, I mean these numbers currently 12 is not going to be improved on because going to D takes longer than that in the first place. 29 could be improved on. A to D is 20 plus D to C is 4, so that makes 24, so that does get improved on. 29 is 20 plus 16 is 36, that doesn't, and then 11 can't be. Just keep going. I'm not going to voice over this again because it's just the same thing. You end up with all these numbers. If you want to, just pause the video and get them done yourself. You end up with all that, and you have your answer. Cool. So then it says it does it one more time, or is it two more times, I guess? Yeah, because it's doing E and F. So it does it a couple more times and you get all this. Using nearest neighbor, starting at E, finds two Hamiltonian cycles. So starting at E, your two choices are either to go to C or to F, since they're equal distance. So we'll start with two routes there. Let's do this C one first. So once you've gone to C, the shortest route is to D. Once you're at D, the shortest route is to F. Once you're at F, the shortest route is to A. And once you're at A, the shortest route is to B. And then you need to go back to the start again, so then we need to go to E. If you do the E to F bit, so we go to F first, then we go to A, then we go to B, it looks like. Then we go to D. Then we're going to go to C, and then we need to go back to E again. What you should do when you're doing this is write down the numbers above them so that you don't have to look in the table again. But if you do that, you'll get all these numbers which add up to that, and then all these numbers add up, or distances add up to that. The better upper bound is this one here because it's the lower of the two. So the ECF one is the better upper bound. Question number 4 then is about big M method, simplex method. I was kind of hoping when I did this that this would be the only simplex method question, and then it turned out there was a second one of them, which is just absolute garbage. So anyway, we're doing this first. Let's actually let's first write what they want us to do. So we've got 2x plus 3y plus 4z is less than or equal to 13 because they've added in a slack to put it in the table, so that must be a less than. And then this row says x minus 2y plus 2z is greater than or equal to 8 because they've added in an artificial and taken away a slack, so that must be that way around. And then this one is just 3x, no y is minus 4z, and again it's greater than because there's an artificial, so we get that. And then there's two things we could be being asked here. We could be asked to maximize this where these signs have swapped over, or if you don't want to swap the signs, you can just consider minimizing that. And those are the two things that are possible to put in. Obtain the most efficient pivot to start with. Well, M is a big boy, so these two numbers are definitely positive. So that's the only negative one here. So we'll start here, we'll do some theta values by doing 13 divided by 2, 8 divided by 1, 12 divided by 3. 12 divided by 3 I think is the smallest positive one, so we'll pivot from here because it's got the smallest theta value. Excellent. So now we've got some, what is this even called? Critical path analysis, is that it? Anyway, let's start with here. We're going to have to do a precedency table. So A, B, and C don't rely on anything. D relies on A getting done. E relies on C getting done. F relies, where's F? There it is. F relies on C getting done as well. G, where's G, relies on A because of this dummy variable B and E. H relies on A, B, and E again. J, which is here, relies on G and D, it looks like. And K relies on, well, because of this dummy, relies on D and G and H and F, which I just tried to put in alphabetical order, but then realized that H and G I don't think are in alphabetical order, but whatever. So that's that. So given that x is between 4 and m, state the largest value of m. Well, x actually appears twice in here. And the fact that this 7 goes to a 16 means that x has to be less than 9, or equal to 9. If x was 10, this could not be a 16 under any circumstances, it would have to be a 17. Likewise here, x could be 10, but the smaller one of those is 9, so we'll go with 9. Complete diagram 1 show late event time, so we start here, and then we pick the smallest value we can going backwards. So obviously here the only way to get there is 15. The only way to get here is just take away 6 to get 16. And then it gets a little bit more interesting. You can either go take away 3 to get 12, or you can take away 5 to get 11. We take the smaller, which is 11. This feels weird to do, but it's just going to be 15 minus x. This way is either 16 minus x or 11 take 4. But the reason 11 take 4 is 7, and we know we need to put a 7 in here because we can't put anything lower in this box than we can in this box. So if 16 minus x was somehow lower than 7, which it isn't because of this, what we just said, it just must be a 7 anyway because this box must match that box at the most. And then we just take away and we get 0 back there, and we'll have our answer. And the critical values, or critical activities, sorry, are ones such that you go from, you have equal numbers in both these boxes, and the amount of time to get from this to this is this value here. So for example, 11, 11 to 11 to 16, 16 makes H critical. If it was 11, 11 to 17, 17, H wouldn't be because the distance between those wouldn't be 5. But it is, so that's fine. So the critical value, critical activities, I think, is C, E, H, and K. And that's good. Float for G, the float is this number minus this number minus this number. So that's going to be 1. And yeah, the question goes on. So it gives you a resource histogram here. This question is really, really hard. It's asking you to see how high each rectangle is. So A is 3 high. Just going to talk you through this slowly. B is 2 high. C is 1 high. D is also 2 high. And then you just keep doing that. Draw a Gantt diagram for the rest of this. So when you're drawing Gantt diagrams, you just draw the critical path first with all the critical activities. So we have all of that, and it gets to 22. And then what you do is you put in all the rest of them. So A isn't critical. It takes 4 hours, and you can start at time 0. But it can take as many as 5 hours after that, and you're still fine. So you shade in going to the hour 9 to represent the last time that you could theoretically do that by. For B, again, you start at 0. It's 5. It takes 5 hours, but you can also, that can take up to hour 11, and you're still fine. For the next activity, so A, B, C, D is the next we need to draw in. D can only start at hour 4 at the earliest. Notice how I've changed this to a 9, because actually D and F take X hours, but the resource histogram tells you that F is 1, 2, 3, 4, 5, 6. So F is 6 hours long. So X is 6, and then this was 15 minus 6, so now it's 9. So I know this is 9 here, which is how I got that A ending point there, I forgot to mention. And okay, so anyway, D is 6 hours long, so that's 4 to 10. But you can finish as late as hour 15. Then we go to A, B, C, D, E. F is the next one we haven't got, which starts at hour 7 at the earliest, takes 7 hours, can finish as late as 16. G is the next one, can start at hour 11, only takes 3 hours, can finish at 15. And I think finally A, B, C, D, E, F, G, H, I. Where's I? What? Anyway, so they've missed I, so we get to J, which is 5 hours, and then you can finish that, 7 hours, and you can finish that an hour late if you want to. And we'll get this picture here, so that's good. Question number 6 is a really weird question on algorithms. Firstly, they just want you to do an algorithm, which I don't think I've seen actually before. So you input the value of n. N is 5, so we input n is 5. Let A be 1, let B be 5 minus 2, let C be B, and then let A be A plus 1, or A is, this just feels gross to read, doesn't it? This is the price you pay when you do decision. You have to read absolute garbage like that. So 1 plus 1 is 2, so A is apparently 2 now. B is B minus 1, which is 2. C, is 3 plus 2 times 2, which is 7, plus 2 minus 1, 1, so that's 8. And then if B is greater than 0, which it is, you go to step 6. So you let A be A plus 1, so that makes it 3. B is 1 less, you work out this again, you get that. And then B still is greater than 0, so you go back to here. That goes up to a 4, that goes to a 0 now, and then you find out this, you get this. And B is now fine, so output C is 16, and we stop. Okay, that was just weird. We have weights of 10 arcs here in figure 4. Here they are. And then we have to do a bubble sort here, so I'm not going to do all the bubbles, obviously. I'm just going to write out the last list at the state of the list. So we bubble this, nothing happens. We bubble this, nothing happens. We bubble this, and those two swap over. We then bubble 23 and 24, and they swap over. We then bubble 13 and 24, and they swap over. So the 24 is just tracking this way. Swaps again, stops here, but then those two swap. So the 24 is going to go there, and then those two are going to swap. And everything else just shoves forward a little bit. Then bubble those, nothing happens. Bubble those, they swap. Bubble those, nothing happens. The 21 and the 23, that is. Bubble those, and the 13 goes there. So that's what's happening here. Bubble those, the 23 is here now, isn't it? So bubble those, and the 15 goes there. Bubble those, the 23 goes there, which finally stops here because 24 is bigger. Bubble those, and they swap, and then bubble the 24 and the 28, and nothing happens. Go back to the start again. Bubble those, they swap over. Bubble 17 and 21, nothing happens. Bubble those, they swap over. 21 goes to here when it bubbles with that, then to there, then nothing, then those two swap over. You can write this out as you go along, it's easiest. And then those two will swap, there will be a 23 here, which means those won't swap over, and you'll be left with this. Then finally, this is fine, swap those over. 17 swaps with 15, and then everything else, and then those two swap finally, and everything else looks good. Then finally swap those two, and we end up with our final list. Which I think, according to the mark scheme, you just have to, this is the final pass when those two swap over each other. but then you have to run through this again and go, okay, good, and you're done. And you write it out again, maybe. I don't know. I don't know whether that's actually worth doing. But the mark scheme did it, so I just added it in. Find the total number of comparisons. Now the idea here is when you do the first pass, at the end of the first pass, when you write down the new list, the biggest number must be at the end. Because even if the biggest number, like pretend this was a 57, or then when you do bubble sort, it would swap with this, then it would swap, 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 and it would guarantee you to be at the end. And then if you know that's at the end, when you do your bubble sort for the second list, you actually don't need to look at the last two because you know the biggest is at the end. So, okay, in the first pass, you need to do 1, 2, 3, 4, 5, 6, 7, 8, 9 bubbles, maybe. But in the second pass, you only need to do a maximum of 8 because you never need to bubble these two because you know the biggest is at the end. And likewise on the next pass after that, just for the same reason, the next biggest number must be in this position, so you don't need to bubble these two or these two. So you only have 7 comparisons to do. So we had 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3, plus 4, because remember that was just the repeated list at the end. That was just the final answer list. So plus 4 comparisons to do, and we end up with 39. Now, worst case scenario, maximum number of comparisons you'd have to do is 9 plus 8 plus 7 and so on. And then it just so happens that you never get to your correct order all the way until the last pass at 1. And so you just add up all those and you get 45. It's given the maximum total number of comparisons required is this, and where lambda is a constant. And now determine what it is for 50. Now, all we need to do here is solve for lambda, because then we can just put 50 into here and we'd be done. But we know, for example, firstly, we know if you have 5, if you know n is 5, you know the maximum number is 45. I didn't think of that at the time. I just said, if n is 3, now I said, well, what about if n was 1, but then you get a 0 here, and that's not cool. If you try n is 2, you get a 0 here, so you can't really use it. But if you try n is 3, so just imagine there are 3 numbers here. For the first run of bubble sort, you do one comparison and then a second comparison, and then the next run, you don't need to compare the last two, so you just do one more comparison, and you have 3 comparisons in total. So we can just shove that result into here. 3, the total number, the largest number, maximum number, is equal to this with just 3's put in there, and you get lambda as an eighth. And then you can just put lambda as an eighth into here with n is 50 to solve your question, which you get this. If you used 45 and n is 5, then you'd also get the same result with this, and then you get this, and you'd be fine. Last question is on simplex algorithm, which is just, isn't that magical? It wants us to fill in this table here, so we're going to rearrange this. Well, firstly, we can say we're looking to be underneath that line, so that's less than or equal to. Then we can rearrange it. Then we can shove in a slack variable to make it equal, and that gives us what this line would be. Right, we're going to put an S1 here. We're going to put -2, 1. This will be an S1. We'll have one of those, and then a bunch of 0, because those will just be the other slacks, and then the value 1. I won't do that right away. I'll firstly say we want to be underneath this line as well. Rearrange. It's already rearranged, which is nice. We just need to add in the slack. Here, again, it's already rearranged. We want to be underneath it, so we're just going to add in the slack immediately. And here, lastly, again, we'll just add in the slack straight away. And then we can fill in the tables exactly like I said. So the slack's there, and then just fill in all the coefficients as you go along with the value at the end. And we end up with our first table. P, we're trying to maximize this, so we just swap those two coefficients around because we want to put those on the other side, essentially. And we get -1, -k, and then just a bunch of zeros. So that's the initial tableau. Of course, it doesn't matter which order you fill in. These, it's very unlikely that you put S1 with this one and S2 with this one. So there's a bunch of acceptable tables for that question, including hopefully the one that I've done. Now, they've done some simplex algorithm, and the reason they've partly done this is just because that means everyone's now using the same table. But they've done a couple of iterations. They've got this. They want us to do some more iterations. They want us to do one more iteration to get another answer. First, it wants to state each value after 7 iterations. So clearly S1 is 1, X is 2, S3 is 22, Y is 5, and then if it doesn't appear in this, you just say it's 0. So S2 and S4, that'll be just 0. Good, and then this is not optimal, so that means apparently one of these two things is negative. Now this can't be negative. It says in the previous slides that P was a positive constant, so this must be the negative one. So we'll start here, we'll do 1 divided by a fifth, we'll do 2 divided by this, we ignore negatives. Well, when I say we ignore negatives, we just completely discount this row from existence when we're choosing our pivots if there's a negative here. 22 divided by this, and then 5 divided by this. The smallest positive one, like I said, ignoring negatives, the smallest positive one is this one. So we're going to pivot here. So let's make this into a 1 by just timesing this entire row by 5. And now we've sorted out S4, so S4 can go here, because it's now a nice little 1, and we're going to make everything else 0. So here, okay, so how do we make this 0? Well, if we take this and we add in 2/5 of that, I think this will be 0. So take this, add in, this is now R1. I know I've called it 5R1, but this is now R1. So if I do 2/5 of R1, I get 2/5 here, which if I add to that, I'm going to get 0. So that'll give me a 0. This just stays as an X. Obviously, if you've got zeros, then everything's nice and happy. You can figure this out if you want to. I'll just do one example. So this one here is going to be 1/5 plus 2/5 of this. 2/5 of this is minus 6/5. 1/5 minus 6/5, I think, is minus 1. So that's where that comes from. And likewise, all those. Next one, we need to make this into a 0. So I think we're going to have to add in, it looks like, what is it? Minus 12/5 of this. Minus 12/5 of that is minus 12/5. Add in 12/5, and we're going to get to 0, so that's good. So it's going to be this minus that. Again, just do that for all of them. The zeros end up being nice, at least. We get this. Next one here, again, we want to make this 0, so this is a bit nicer. Just do this minus 1/5 of this row. I think we'll get it pretty quickly. 1/5 of that is 1/5. 1 minus 1/5 is 0, so that'll get us that pretty quickly. Again, do the same thing for the whole row. You get this. And then finally, the most difficult row. How do we make this into a 0? Well, this is just a 1, thankfully. So if we just times this row by this and take away, I think we'll be good. Because if we imagine doing this bit here, this minus itself times 1, well, minus 2/5 minus minus 2/5 cancels for 0, and then 1/5 k minus 1/5 k will also cancel for 0. So I think we're going to have to do that operation, which thankfully there are some zeros which are going to make this okay. This I would suggest maybe doing some working for. I don't think I have, thinking about it. No, actually, because there's just a 0 hidden there. So we're going to do 5 times this, and there's just 0 minus ands. So 5 times this is minus 2 plus k, and then 0 minus that is just 2 minus k. So that's where that comes from. This next one I decided to do some actual working for. It's going to be this minus this into there times this, so the minus 3 goes into there. Multiply that out and do the maths, and you get this. This one is just 0, so that's fine. This one is designed to be 0, so that's good. And then lastly, 5k plus 2 minus this times 5, I think is what I need to do. That multiplies out, it simplifies to that, and we have this table. You should hence determine the range of values for p. Now, the fact that this wasn't optimal means that that's less than 0. So that's where I'll start, I guess. You can solve that to make this, so k is less than 2. Now, the fact that this is optimal means that that's greater than or equal to 0. So therefore, k is greater than or equal to 1, and therefore we have this range. And now this is our profit, so state the possible values for p. Well, if k was 1, then this is 8, so we're greater than or equal to 8. If k was 2, this will be 12, so we're less than 12, so the profit is in between those two. That's the whole paper. Thanks for watching.